Let's start by creating a working directory that will house our checked out code. Let's now change directories into that directory. We'll be working with two project directories that I've previously built. The first can be cloned using the following command. Now let's change directories into our MIGS-CICD directory. Now let's start our virtual machine. To bring up our VM called MIGS-CICD, we can issue a Vagrant up MIGS-CICD command. With the magic fast forward, we'll breeze through this setup process. Once our VM with pre-installed tools is up, we can SSH into the VM with Vagrant SSH MIGS CICD. Since this is a pre-built environment bundled with a variety of common dependencies for building a pipeline, we should be able to verify that tools are already installed, such as Ansible, with the Ansible ---- version command, and Docker with our Docker ---- version command as well. We can also check the version of our Docker-Compose install with the Docker-Compose ---- version. To get a list of packages installed, we can run dpkg ---- get selections. As you can see, many dependencies have been pre-installed in our working virtual machine for us to leverage without manually installing them each time we need to start a project dependent on these resources. Since the aim is to create a continuous integration and continuous deployment pipeline, you can see how having everything automatically scripted into our VM is critical in achieving this goal. Let's now change directories to our Vagrant directory. A few observations when we ls the directory are that it is showing the same directory structure as seen from outside of the VM environment. Now let's clone our second directory. We'll clone this directory into /Vagrant directory. The base contains several configuration files that we'll use to build our pipeline further, including our MIGS-base directory. Let's move on to the next step. For steps 2 and 3, we'll run the pre-deployment tests, compile and package our code. We'll use a pre-built Docker pool MIGS-base-tests container that has both the back-end and front-end. Let's set unrestricted permissions for our MIGS-base directory before we start building our test container to avoid accessibility issues as we continue through the demo build. The next steps involve leveraging a predefined Docker file.test file to build our test containers. To build a test container, we can issue the following command: sudo docker build -f dockerfile.test -t 10.100.198.200:5000 migs-base-tests, and then period. As you can see, all the packages are being pulled as defined in our Docker file, .test file, for building our test containers with close to 30 steps. The container, when finished, will be equipped to support tests leveraging Node.js, Gulp, MongoDB, Scala, with just over 1,858 packages added. Now let's run all the pre-deployment tests and compile the Scala code into a jar file, ready for distribution. To do this, we'll issue the following command: sudo docker-compose-f docker-compose-dev.yml /run --rm tests. If the compiling step successfully completed, you can verify this by navigating to the Scala-2.10 directory to find the resulting makes-base-assembly-1.0.jar file. We can do this by issuing the ll-target/Scala-2.10 command. With all of our tests passed and jar file created in steps 2 and 3, we can build a container that will be deployed from our pipeline into a production environment. To build our container, we'll issue the following command: docker build-t 10.100.198.200 $5000 /migs-base . Now let's try running the container we just built. Before running it, let's start the database container required for our service. The following command starts our database container: docker run -d --name migs-db mongo. In this case, the -d allows us to run containers in detached mode, meaning it will be run in the background. The --name migs-db gives the container a name, otherwise Docker will assign one on its own. The last argument is the name of the image we want to use, which is Mongo. Now let's start the container we built. In this argument, the 8080 exposes port 8080 linked to migs-base-db container. The link command links the two containers. Let's verify our environment variables are running by entering the running container. We can do this by using the docker exec -it migs-base bash. The -it tells Docker we want it to be listed iteratively. Typing env grep db will list out all of the environmental variables associated to this DB. Once we verify this, we can exit. We can also verify that the container is running properly in Docker by typing docker ps-a, which will list all of the containers, including those we just started. Now that we've verified our containers are working properly, let's remove the MIGS-base container and its dependencies, freeing up MIGS CICD server to do continuous development. We're now ready to push the Docker container to the registry. For this step, we'll leverage the Docker registry to conveniently store and retrieve containers. We've already run it with the MIGS CICD VM we previously created. With the MIGS-base build, we can push our build to the registry. That will allow us to pull the container from any place that can access the MIGS CICD server. By pushing our test container, we ensure that we will not have to build it from scratch again to use it in our pipeline. All pushed images are stored on our host, the directory registry, and they do not depend on a VM running. We can now safely destroy all of our VMs as long as we've made sure our containers were successfully pushed. Destroying our VMs loses all of our work. At this point, we're just over the halfway mark and ready to deploy our container into our production server. To deploy our container into our production server, we'll start by bringing up the VM node we'll use for our production build. To do this, we'll issue the following command: vagrant up MIGS CICD. Once our VM is up, let's log in to our VM. Let's navigate to our /vagrants/Ansible directory. From here, we can review the Ansible playbook, which contains arguments with paths to inventory files with lists of servers. To run our predefined playbook, we can issue Ansible-playbook/vagrant/Ansible/prod.yml-i/vagrant/Ansible/hosts/prod. To verify tasks are running with an OK flag, we can issue the following playbook command: Ansible-playbook-prod.yml-i-hosts/prod. Let's now pull down our Docker Compose configuration file that specifies how the container should be run. With docker-compose.yml downloaded, we can run the Docker Compose app target. Now let's run the Docker Compose target app linked container, DB, deployed as part of the production server. To allow invoking remote Docker APIs, let's disable security in the /etc/default/docker directory. Here's what the full command string looks like. Now let's confirm both containers are running. As we can see, both containers are running there. Docker assigned a random port to the service internal port. Now let's find out what the actual port is by issuing the inspect command. The output is very long, but the important part that we're looking for is attached to the network settings.ports section. In our example, we see it shows host port 32768 mapped to internal port 8080. It should look something like this. Another way to view this information from a GUI standpoint is to use Docker UI. We can access this GUI by going to http://10.100.198.200:9000 in a browser. If you want to use this feature outside of the host computer, you'll need to use RDP or VNC for remote access. A quick review of tools. In order for the next several steps to make sense, we should review the role that a few tools play in a CI/CD pipeline. We've already gone over tools to decouple our application for agile deployments through the use of tools like Vagrant and Docker containers. We've also touched on configuration management and orchestration tools like Ansible that we've used to automate our deployments. For the steps that follow, we'll be diving into the use of service discovery tools like Console and etcd used to script everything from server setups through to deployments. We'll also use a common tool called Nginx as an HTTP and reverse proxy server to help us with load balancing and TCP proxying. Let's take a look at a simple implementation of Console's management features in the MIG CICD VM that we have up and running. To do this, we can leverage our predefined playbook, which contains our service discovery and proxy resources. If you've never used Console, you'll find that it can be used as a very convenient way to monitor the health and clustered nodes and services. We can, for example, monitor memory usage, and if it reaches a certain threshold, move some services to a different node. Many examples of its use can be tied to preventative actions performed before a disaster would happen. On the other hand, not all potential failures can be detected in time for us to act on. A single service can fail. A whole node can stop working due to hardware failure. In these cases, we would prepare to act as fast as possible by, for example, replacing a node with a new one and moving failed services. Console Web UI comes at no configuration cost, since all that is required is to specify the directory where the static files are. Let's quickly do this with a pre-configured Ansible playbook I've already prepared. From our running MIG CICD VM, let's issue Ansible-playbook/vagrant/prod2.yml-i/vagrant/ansible/hosts/prod. Let's now pull down the Docker Compose configuration file that specifies how the container should be run. With Docker Compose.yml downloaded, we can run the Docker Compose app target. Now let's run Docker Compose target app link containerdb deployed as part of the production server. To confirm provision node via console, you can navigate to http://10.100.194.201:8500/UI in your browser. Now let's integrate the service and confirm that Nginx is aware of our service. If we do a quick curl test, we'll find that it is currently not aware of our service and will return a 404 not found message. Let's exit. Now let's log into our production node. Let's pull down a few resources. Now let's launch our template. As you've probably already noticed, we did much of the container integration process already. To go through it, we entered the prod node and downloaded the includes files and upstreams template from the code repository in GitHub. Then we ran console template that fetched data from console and applied them to the template. The rest is Nginx upstreams configuration files. Note that this time we added the third argument docker kill-s hup nginx. Not only that, console template created the configuration file from the template, but it also reloaded Nginx. The reason that we did those commands from the prod server instead of doing everything remotely like the previous steps lies in the automation. The steps we just ran are much closer to the way we'll automate this part of the process in future steps. Now let's launch our post-integration test through port 80. Launching our test through this port is the equivalent of launching without a port at all, since it's an HTTP port. The final step is to push our container to the registry for reuse. The good news is, after all of our work up to this point, pushing the container is a simple task, similar to what we did in step 5. We'll use the command docker push 10.100.198.200:5000/migs-base-test. And we can exit. As we saw in previous steps, we can destroy our VMs now that we've pushed our built containers to the Docker registry. So what does all this mean? All the manual work done previously was meant to show you the individual steps that were manually involved for creating our CICD pipeline. However, the Holy Grail and what the previous steps have led us to understand is that we can automate the implementation of those manual steps. To demonstrate this automation, we'll revert back to using Ansible. The only step we will not automate is checking out the code. The reason being that Ansible is not meant to monitor code changes in GitHub. Let's quickly show this by going into the Make CICD prod node. We'll be using an Ansible playbook to perform the automated steps done previously. To review the configuration we're using to automate our processes being used, you can review the service.yml and main.yml files. Let's run our service.yml playbook with the inventory pointing to the host prod file and a few extra variables. For each task that has manually been run previously, there will already be an OK flag because it's been run before. This step will take a lot of time, which we should expect given the amount of work that it's performing for us. At the moment, we have only this service. If there were more, they could all be deployed with the same playbook by changing a couple of variables. This playbook not only manages to automate the full deployment, but it also provisions the destination server. The first playbook was done against an untouched Linux server, so Ansible made sure that everything needed for the deployment was properly configured. Though the results are not perfect, they're a good start. Feel free to repeat the execution of the playbook and observe the differences when compared to the first run. You notice that most of the Ansible tasks will be in the status OK since there was nothing to be done, and that the playbook runs much faster. Once again, to reiterate, this is a first cut and there may be some pieces missing, but close enough for now. Once it's completed, feel free to navigate to http://10.100.198.201:8500/UI to review the console UI that we had previously set up manually. Once you've completed this, you can exit and destroy the VMs. For now, I'll leave you with this introduction to creating a CI/CD pipeline. Thanks for hanging in this long.